So let's carry on with our discussion of blast waves and the Sedolph-Taylor solution. And just to remind you that we are talking about a supernova propagating into the interstellar gas, and we have a shell of radius rs, and it's propagating outwards at some velocity us, which we've just related to the unshocked medium as 2 u0 over gamma plus 1. And we also know that the density of the material inside, so rho 1 is equal to gamma plus 1 over gamma minus 1 rho 0. And we've related the radius of the shell, which we call rs, or delta r, I mean. So the shell itself, the thickness of the shell itself, delta r over r, is given by 1/3 over gamma minus 1 over gamma plus 1. So that's just to remind us of a few things that we might need to know. So now let's think about the pressure exerted by the shocked gas, which is now hot, and it's pushing out onto the interstellar medium. So we can imagine that there's a pressure just inside the interior edge. So we defined an interior pressure, P1. And we also can talk about the mean pressure, P bar, which is the overall mean pressure inside this shell itself. And we can describe the mean pressure as related to the pressure just inside the surface by some factor, epsilon, that's scaled with that. So that factor would presumably be less than 1, is the mean pressure inside that area. And we can relate that back to P1, to P0, because, which is the exterior pressure, the pressure before the shock passes over, because we know that from Rankine-Hugoniot conditions. And so we can say that epsilon to gamma plus 1 rho 0 u0 squared is the mean pressure inside. So we're relating the pressure in that shell to the external initial density and velocity. Okay, now this pressure does work. It does some work on the medium. And what can we learn about that? Well, we can say that epsilon P1 times 4 pi rs squared, so the pressure over some area, should balance out some mass times the shock speed, and that one is the rate of change. Writing problem. Rate of change of momentum. So the pressure of that shell applied across some area of the surface area of the shell itself will be balanced by the rate of change of momentum of that shell and its mass. Now, what is the mass of that? Well, the mass is just given by 4 pi on 3 rho 0 rs cubed. So that's, again, where we've said that earlier that the mass inside the shell of delta r thickness was all of the density was cleared out from inside that shell and piled up like a snowplow pushing against the interstellar gas, piled up into a thin shell, and that has mass. So this is the mass in the shell assuming all of rho naught was swept up. And the analogy that I made of a snowplow is in fact a very commonly made analogy when talking about supernova explosions, where we refer to the snowplow phase of their evolution. And that's the part that we're talking about now, where they're piling up all of the gas that was initially there. Okay, so from here, what can we say? Well, we can say that the pressure inside the shell times the area, epsilon P1, 4 pi Rs squared, and that's pressure inside the shell times surface area. And you might imagine that's a force, because it's a pressure times an area, is equal to the time rate of change, ddt, of the mass, 4 pi on 3, rho naught Rs cubed, times the shock velocity, and that one is the rate of change of momentum. So this is how this shell is sweeping up mass and its momentum is changing. So from there, we can recall a few things. First off, let us recall that the shock gas velocity is given by 2 over gamma plus 1 times the initial external velocity. So let's rewrite epsilon P1 4 pi Rs squared is equal to d dt times 4 pi on 3 rho naught Rs cubed to u naught over gamma plus 1. So we can cancel out some terms from that. We can also remember that P1 can be related to rho naught. So we recall also that P1, maybe there's a better way to write that so it's a little clearer. And P1 is equal to, oops, not epsilon, sorry, is equal to rho naught over gamma plus 1 times 2 u naught squared. Okay, so are we good from there? So let's take that forward and enter in some equations and cancel some things out. So from here, we can say that 2 epsilon over gamma plus 1 times rho naught u naught squared 4 pi Rs squared is equal to d dt times 4 pi on 3 rho naught Rs cubed to u naught over gamma plus 1. Whew, that's a big equation. So what things can we get rid of? Well, we can get rid of a few things. We can get rid of 2 and a gamma plus 1 and a gamma plus 1 and a 2. We can cancel out our rho naughts because rho naught is not dependent on time. We can cancel those out. We can cancel out our 4 pi's. And we are left with a slightly simpler looking equation, which is that epsilon u naught squared rs squared is equal to 1/3 d dt times 1/3 rs cubed u naught. Okay, so all we've done so far is to say that the pressure inside the shell times the surface area balances out the rate of change of momentum of the shell, and we've come down to this place here. So let's pause there, pick it up again in our next lecture.